Alrighty, folks. Before we get into some real problem solving, I wanted to go ahead and provide you with at least some brief examples on how to approach problems in this chapter in work, energy, and power. So let's look at a simple example here. A child pulls a wagon that weighs 98 newtons with a force of 10 newtons to the right and 20 newtons upward. He pulls it a distance of 2 meters. How much work is done on the wagon? All right. Well, this is definitely a problem where I want to draw a picture. So here's my wagon. Here's the child pulling, and as you can see, he's pulling sort of at an angle, both upwards and to the right. Now, we were given a lot of information in this problem. We were told that the wagon weighs 98 newtons. That's one force. He's pulling up and to the right, up with a force of 20 newtons, to the right with a force of 10 newtons. And I can actually deduce one more force if I look at my free body diagram. So here I've got the wagon. Its weight is downwards. I've labeled one of the pulls to the right, one of the pulls upwards. But is this wagon accelerating downwards through the floor? No, it's not. It needs a balancing force, and that pull of 20 newtons does not balance 98 newtons of gravity. But if we add another 78, together 20 and 78 can balance 98. 20 plus 78 is 98. So I know that the normal force, it covers the balance, it covers that remaining balance of 98 minus 20. It's going to be 78 newtons. Because the child's pulling up a little bit, the floor doesn't have to push as hard. And so the normal force is 78 newtons in this problem. Nonetheless, we have a bunch of forces. And we're asked how much work is done on the wagon. Well, work is given by FD, force times distance. So the question becomes, which force? And if you recall, it is the parallel force. The force that is parallel to displacement is the force that does work. And this wagon's being pulled to the right, so it's going to be that force to the right that does the work. All the forces up and down do no work. They are perpendicular. Only the force that is parallel does any work. So we can compute that pretty quickly once we've identified that. Work is force times distance, 10 newtons times 2 meters, 20 newton meters, or we could call that 20 joules. But the most important step in this simple example is recognizing which force is parallel. And there's a lot of tricky questions that can be asked like this. So for instance, if I'm holding some object in my hands, gravity pulls it downward, my hand provides a force upwards. If I move it side to side, am I doing work on that object? No, I'm not. My force is upwards, and my motion is side to side. This does not do any work. If I lift it upwards, now I'm doing work. My force is upwards, I'm lifting it upwards. And similarly, if I move it downwards, I also would be doing some work on it. In that sense, it's sort of a negative work. I'm lowering its potential energy. But nonetheless, my motion needs to be in the same line of the force. Moving something side to side while holding it in the palm of your hand does not do any work. There might be frictional forces on my hand that cause it to come along. Those are doing work, but in terms of my palm pushing it upwards, that does no work whenever I move side to side. All right, so that's one quick example of how to compute work. I always want to highlight how this whole parallel force business actually looks. And I've got a worksheet that I'll be handing out that really drills this in. Let's take this simple example a step further. If the child's wagon started from rest, what's its final velocity? Simple enough, right? Well, this deceptively simple problem, as you'll soon see, has several steps. Well, we're trying to come up with its final velocity. Velocity is motion, so we should know that kinetic energy is involved. And this also has nothing to do with potential energy. The wagon rolls along at the same height. Because of that, I can use the work energy theorem, and I can see that the amount of work done on the wagon is going to be equal to its change in kinetic energy. Kinetic energy, remember, is given by 1/2 mv squared. So if something's not moving, if v equals 0, the kinetic energy is 0. That means that initially, since the wagon started from rest, the kinetic energy is 0. So looking at our change in kinetic energy, final minus initial being 0 means that work is going to all go into that final kinetic energy. Whatever work we did, all of that energy was transferred into its kinetic energy. So the work should equal 1/2 mv final squared, or work equals 1/2 mv final squared. That's our equation we want to start with. And we're trying to solve for that final velocity. So let's do some algebra. We are first going to multiply by 2 to get rid of the 1/2. So 2w equals mv squared. We want to get to that v final, so we got to divide by m. So 2w over m equals v final squared. Next, we take a square root. That is how we get rid of squares. We haven't had to deal with that yet in this class. At least I don't think so. When you have a squared, you get rid of it with a square root. So we take the square root of both sides. We're left with the square root of 2w over m on the left. And on the right, we have finally reduced it to simply v final. So our equation is v final equals 2 times the work over the mass. And I can go to plug in numbers, but I'll realize quickly, wait a second, I never was given a mass explicitly. But it was given to us implicitly. And this is a trick that you're going to have to use throughout the rest of the semester. We weren't given a mass, but we were given a weight. And mass and weight are closely related. Mass is part of the definition of weight. Weight is the same as the gravitational force, which is given by m times g. And we were given the weight. We were told that this wagon weighs 98 newtons. That is, that the gravitational force should be negative 98 newtons. And of course, we know what the acceleration of gravity is. G equals negative 9.8 meters per second squared. So we can solve this equation, F equals mg, for m. Divide g over to the other side. M equals F over g. The force of gravity divided by the acceleration of gravity gives you something's mass. So negative 98 newtons over negative 9.8 meters per second squared, that gives us 10 newtons over meters per second squared. Well, what's a newton? A newton is a kilogram meter per second squared. That leaves us with meters per second squared on top and meters per second squared on bottom. Those can cancel, and the only units remaining are kilograms, which does indeed look like a mass. So we can take the weight and we can use a weight and solve for something's mass. So we now know the wagon has a mass of 10 kilograms. We take that back over to our equation and plug it in. We've got 40 joules up top. That came from 2 times 20 over 10 kilograms. And all of that is under a radical or a square root sign. 40 over 10 is 4. Units are joules per kilogram under the radical. The square root of 4 is 2. And the units we're left with are the square root of joules divided by kilograms. That's kind of messy looking, so let's think about it a little more. The square root of joules over kilograms, well, joules can be written out as kilogram meter squared per second squared. The kilograms on top can cancel with the kilograms on bottom, and we're left with the square root of meters squared over second squared. The square root cancels each of those squares, and we're left with simply meters per second, which makes sense. It is a velocity. Meters per second is a familiar unit of velocity for us. But the point of this exercise is that we can do something like take a work and figure out how it gives something a velocity through arguments with energy. We didn't think about force and how force caused an acceleration and that acceleration changed the velocity. We could have done all of that. Instead, we came up with the amount of work done, related that to the kinetic energy, and then solved for the velocity using energy. So we'll see many more examples like this. We'll see energy changing from one form to another. In this one, we just directly added energy to something via work. We transferred it via a direct force. But we'll see plenty of examples in this chapter. We'll see kinetic energy coming from potential energy and vice versa. We'll see springs being compressed and then launching something like a toy dart gun. You can compress a spring, and then when you release it, it can launch a projectile. There are plenty of examples will work, and energy is a very, very powerful tool when it comes to physics. So I really like this chapter. Some people think it's tough, but you could say that about pretty much any subject. Enough practice and you'll get it. I personally really like it, find it fascinating, so it's one of my favorite chapters. We'll get into more examples soon, but I wanted to give you guys a little bit of a teaser, a couple of short examples to get started with. So until next time, take care.